And then because of the cathode you have here, you accumulate negativity. Now inside become more positive. So minus 90 to minus 80. And nothing happens. And then it goes to minus 70. That's a 20 millivolt depolarization, enough to do what? Enough to open the sodium channel. And open the sodium channel, now the sodium come in. Once the sodium channel open, sodium come in, inside now become 20 millivolts. Remember? So you say, yes, action potential is generated because it changed from minus 90 to plus 20. Alright? But that action potential generated here, if you stay here, it doesn't do any purpose. It has to propagate. So the next question, how does it propagate? It does this way. This is now active zone, so plus 20 millivolts, right? But the next node around here is a resting membrane, so this is minus 90. Alright, so you have plus 20 here and minus 90 here, next node around here, on both sides. Yes? And the current, of course, go from positivity to negativity. And this is what we call driving current. So this driving current gradually makes next node around here more positive, because positivity is running on both sides. And if this now becomes from minus 90 to minus 70 because of the driving current, well, minus 70, so there's a 20 millivolt difference, enough to open the sodium channel. And now the sodium channel is open, and the action potential now is generated. You follow me? And that's why we say that action potential jumps from one node around here to the next node around here, on both sides. So action potential always, if you activate the action in the middle, it always propagates bidirectionally. That's what we do. That's exactly what you do when you stimulate the action potential. Moves, and it makes it very quicker. It's a so-called saltatory conduction, saltation, and the skipping, and dancing. Okay. Now, if you have a demyelination though, like an Guillain-Barré syndrome, what happens? If you don't have a myelin, I told you myelin is a protective sheath. If you don't have a demyelination, if you have a demyelination, then this is an intact part of the nerve. You have a cathode, and you generate the action potential. Now it becomes 20 millivolt plus. And so this is going to induce driving current, right? To make the next node around here, to depolarize the next node around here to the critical level. But if you don't have a myelin, this driving current will leak out. Yeah? And if this guy leaks out completely, then there will be no change, no depolarization in the next node around here to the critical level to open the sodium channel. And if you cannot open the sodium channel, then you have no action potential. And that is a conduction block. And this is one of the main characteristics of demyelination. Yes? If the leakage is minor, then it does leak a little, but in time, this driving current may be able to depolarize the next node around here to the critical level. Then you open the sodium channel, and you have an action potential, which is fine, but it is delayed because you have to wait longer for the depolarization to arrive at the critical level. And this is a delay of conduction because of demyelination. These are two characteristics of demyelination. This makes very, very good sense, right? There are two other features of demyelination, which I'll tell you more later. Okay, so much for that. And I kind of like the analogy in this solitary conduction analogy, so-called bucket analogy. It's like, this is my bucket, here's another one, which is connected with tube, tube. And if you have this, if you put the water in into this bucket. When the bucket is full, then the prolongation of action potential to the next node around here, and this bucket becomes full, and the next one, and if you wait here, you can drink water. Right? But if you have a leakage, like demyelination, if the leakage is complete, if you activate, if you fill this bucket, if this leakage is complete, you get nothing here. Right? This is a conduction block. But if this leakage is partial, then it takes longer for next bucket to become full. So if you wait longer, you can get water. Right? So this is an analogy to demyelination. And therefore, even if you have a complete conduction block here, if you put water in here and you get nothing here because it leaks out completely, that's a demyelination. But then if you ask your friend, come down and fill this bucket, put water into this bucket, then of course you get to drink water here from here to here. Nothing is wrong. And this is a segmental demyelination. Therefore, if you stimulate this stuff to the side of the region, you get a normal response. And that happens all the time. That's how you know this is a demyelinated conduction block. In contrast, if you have axonal degeneration, what happens? Axonal degeneration is a change of structure of the whole thing. Because of the reason here, you destroy not only the bucket, but also the tubes here. In that case, if your friend put the water into this bucket, you don't get it. But if you ask your friend to come down and fill in the next bucket, he cannot do that because axons are degenerated. And therefore, if you stimulate this stuff to the side of the region, you don't get any response. So that's the difference between axonal degeneration and demyelinated conduction block. Either way, you are weak, but there is the neuroconduction difference between the two, which is very important. That's a basic of neuroconduction study. All right? Any questions about this? Yes?
The earlier diagram you showed the slowing.
Give him a mic.
Yeah.
Your phone.
It's okay. You showed the slowing that happens because of leakage of current. The leakage of current causes slowing rather than conduction block. But if it is all or none, either the current gets through or it doesn't get through, how do you explain at an individual axon level? How do you explain the slowing in the demyelinated segment? In the earlier slide.
Okay, I sort of simplified it as a leakage of current, but it has also a lot to do with the capacity of myelin. And when myelin becomes demyelinated, it has a greater capacity to sort of absorb the current in there. And so that is a little more complicated than what I told you. Yes. Yes?
Just two things. It's very nice presentation, June, how would you do? But looking at that, the anode and cathode, the red to the black, the way when you are stimulating, like neuroconduction studies. So that's one important part. The second thing is that, like demyelinating, you showed, the delayed response are black. Whereas if you got axonal problem, then a decrease in amplitude. Okay, that's important when you're doing neuroconduction study, axonal neuropathy versus demyelinating neuropathy. Axonal, you have decreased amplitude. And we have distal latency prolonged in demyelinating neuropathy. Right, June?
Yes, and that here I am talking about only one axon, right? But when you do the neuroconduction studies, there are hundreds of axons there, and some of them has conduction block, and some of them has degeneration. So there, the amplitude becomes very important, and we'll do that. We'll discuss that a bit later. Yeah, about that. Okay, so let's go to the I have 10 o'clock, is that right? 9:30. 9:30. Oh, I'm already past the time. But I think I need to do a little bit more here. Yeah, so this is analogy. Let me skip this. Because I need to talk about now I need to talk about what you recall. What you recall, right? When action potential propagates, what do you recall? And this is a little complicated, but this is very basic of waveform analysis that we all need. Now, in the experimental setting, now this is a recording electrode. Remember, in order to stimulate, you need cathode and anode. Yes? In order to record, you need what we used to call G1 and G2. And G1 and G2 comes from grid of amplifier, which we no longer use. And so G1 and G2 are obsolete terms. And we now tend to use electrodes E1 and E2. All right? So, but you need two electrodes like this, A and B. Because what you measure here is the potential difference between the two recording electrodes. In clinical electrophysiology, it is not possible, it is impossible to record what is actual voltage under one electrode. You always need to compare to another electrode because the only thing you can record is the potential difference between the two. That's one thing you need to remember. So you always need two electrodes, right? So if this is an active zone, meaning that the sodium channels are open, and this is inside plus 20, and the other is a resting zone, minus 90. You follow? And then this active zone, as we discussed, now propagate from here to here like that. Right? So then you ask yourself, what do we record? Well, if the active zone is under A, and if inactive zone under B, remember here, inside is minus 90 millivolts. And therefore, outside is positive. Electrode B is positive, right? Because it's outside the axon. Here, inside is plus 20, and the E outside is the negative. So now you record the potential difference between A and B, and in this particular setting, A is negative to B. And this is what we now call E1, yeah? E1 and E2. When E1 is negative compared to the reference electrode, then waveform, the trace goes up. That is the definition. You can argue, you can say that I'm going to be different. I'm going to make it, in this case, I'm going to make it going down. And some people do that. Some people, like especially the audio, the brainstem auditory evoked potential people, they make positive and negative difference. It's arbitrary. But in general, in electrophysiology, negativity is up. So when this is negative, this goes up. And when the action potential reaches both A and B, then now there's no potential difference. That's when it crosses the baseline. Yes? And when it moves away, now B becomes negative compared to A, and therefore A becomes more positive than B, then it has to go down like that. So in experimental setting, when you record the action potential propagate, you always record initial negativity and the second positivity diphasic waveform. But this never happens in human recording. Because in human recording, you don't put the pick-up electrode directly on the nerve. So what do we record in human recording? It's always triphasic waveform. And I think you need to understand that it's a little complicated, but let me go through this. Using so-called solid angle approximation, which sounds terrible, but once you get it, you get it, right? All right, so let me try that, and I finish this talk. When this is another axon, just like the one I showed you, right? And what's happening here is this is the active zone, meaning sodium channels are open and inside is positive, plus 20. And this is inactive zone, potassium membrane. Inside is minus 90 millivolts, right? And this positive zone is propagating this way. Now, if you record the same thing using electrode, pick up electrode here and here directly on the nerve, then you record biphasic potential. But you don't do that, because in human, you always have subcutaneous tissue around the nerve. You never put the electrode on the nerve, right? And so there's a subcutaneous tissue, which is called volume, conductor volume, and you are looking at this action potential from some distance, not far distance, near, but from some distance. So the question is, when you're sitting here as a pickup electrode, what do you see? Yes? Well, you see all kinds of things in here, but you can divide that into 3 segments, right? And solid angle, meaning tridimensional angle. And this P has a solid angle which commands distance. But you can divide it because there is the separation between active zone this active zone, sodium channel and potassium channel. There is a section between these two. And so you can divide this solid angle into 3, omega 1, omega 2, and omega 3. Right? Now we're going to take each solid angle separately. Now let's take omega 1 first. When you're sitting here and looking at this, through this solid angle omega 1, what do you see? Well, you see 2 dipoles, one here and the other here. Dipole meaning anything which is polarized. Yeah? This is a dipole because there's a negativity on one side and positivity on the other side. This is another dipole because you have positivity on side and negativity outside. So you have 2 dipoles which share the same solid angle and opposite in polarity. You see that? This is what we call negative dipole because negativity is facing you. And this is what we call positive dipole because positivity is facing you. And these dipoles share the same solid angle, and therefore they cancel, and you see nothing electrically. So this omega 1 is nothing because you have 2 dipoles opposite in polarity sharing the same solid angle. All right? Now if you take omega 3, same thing happens. One dipole which is positive, the other dipole which is negative, sharing the same solid angle, and therefore when you stand here through omega 3, you see nothing. So you can cancel that, right? And that is what we call approximation, right? Now we are left here, omega 2. What do you see in omega 2? Well, you see 2 dipoles, one here and the other here. But this time, they are not going to cancel because both are positive dipole. Positivity here, negativity, positivity here, negativity. Right? In fact, you can count 1, 2, 3, 4 positivity facing you, and 1, 2, 3, 4 negativity away from you. Right? And you can see that this omega 2 solid angle shares the transverse section of this action potential, of this axon. So instead of having two dipoles separated, they said, why don't we put these positivity and negativity on the transverse section, which you can do. And if you do that, you end up with this. See that? And so this very complicated situation can be now summarized with just one dipole, positivity in front. Yeah? So you are now watching this from here, and this one dipole, positive dipole, is moving as it propagates from, in this case, left side, right side. And so when you read a textbook talking about action potential propagate, they often talk about approaching phase of positivity. That's exactly this they are talking about. And this is a depolarization, which is also followed by repolarization. Remember, sodium channel become inactivated, action potential ends. That's a repolarization. And using the exactly same analogy, you can say that there's a second dipole similar to this, but negative dipole, when the nerve becomes repolarized. So when action potential moves, two dipoles are moving, and you're sitting here to watch. The first dipole is positive, second dipole is negative, and often we talk about leading dipole and trailing dipole. And you read this all the time, right? So what happened is that you have, this is the initial depolarizing phase, this is the positive dipole, followed by the negative dipole, this is the leading dipole, and this is the trailing dipole, and they're going to move, and you're watching to see, this is all terminology, grid 1, grid 2. We now use E1, electrode 1, and electrode 2. But E1 naturally initially see approaching positivity, right? And if it is positive, by definition, the action potential will go down. This is how we define it, right? So it becomes positive, and when these two guys come right under the pickup electrode, now this one sees the negative end of both dipoles. That's when you have a negative spike. And then when both of them go away, now you begin to see the end of the leading dipole, which is positive. So now you become second positivity. That's why whatever you record, EMG, neuroconduction, whatever, through a volume conductor is always triphasic, initially positive, then negative spike, and then second positivity. And when you see this waveform, it has a meaning. You know, when you have this positivity, you said, yes, this action potential is now approaching. And when you have a negativity, you said that, yes, it has just arrived under the pickup electrode. And when you have a second positivity, you say, it's now leaving. Right? So when you say two things, I think you need to remember. If you don't remember all the theories at all, you have to remember that action potential is always recorded through a volume conductor. This applies to nerve conduction study and the EMG, anything you do. It's always triphasic. And the initial positivity indicates action potential is approaching to your recording electrode. Negative spike tells you that it has just arrived. And then second positivity tells you that it is now leaving. Now, people often ask me, why is it that the initial positivity is bigger than the second positivity? Well, that's because time course of depolarization and the time course of repolarization is a little different. And that's why triphasic waveform looks like this. Right? So this is a prototype. But there is a variation like this. You know, when you do EMG, you get the fibrillation potential. Fibrillation potential looks exactly like this. Yeah? But you can also see positive sharp wave, which looks just like this. Now, what does positive sharp wave mean? Yeah, when you see this waveform, what does it mean to you? Well, it means here that yes, something is approaching, but it never gave negative spike, meaning it didn't reach to your pickup electrode. And in case of positive shock wave, probably because you have injured the muscle fiber with the tip of the needle, so that actual fibrillation potential begins. But when it comes to the recording side, it cannot give you negative spike. That's what it means. And on the other hand, if you record the same single muscle fiber at motor point, motor point potential, when you go, the tip of the needle goes to the motor point, you record muscle action potential, single muscle action potential initially there. Now what does this mean? Well, it doesn't have a positivity, meaning nothing approached. That means that action potential must have started right under the pickup electrode. And that's what happened when the tip of the needle is at the motor point. That's where the action potential begins. So this waveform has a meaning, right? So that is the take-home message. One, whatever you record through a volume conductor, either with a needle or surface electrode, prototype is always triphasic. Initial positivity telling you that action potential is approaching, negativity telling you it has just arrived, and the next positivity telling you it has departed. And if you have a variation, like if you don't have an initial positivity, that means nothing approached. Why? Well, because action potential happened under the pickup electrode. That's what it means. And that's how we know it's an end-plate spike. And when you're missing the negative spike, it means, yes, action potential approached the needle, but it actually never made it because muscle membrane is damaged, and that's a positive shock wave. I hope this is very clear. Remember, it's a triphasic wave, and waveform analysis is the basic for both EMG and neuroconduction study. Okay? I think it was a good time. Great. Thank you very much. Yeah, any questions?
Thank you, Professor Kimura, for this fascinating lecture and session. Any question?
This is like Japan. When I give talk in Japan, nobody asks a question. But when I give in America, everybody wants to ask a question. But you can talk to me anytime.
Can we begin the second lecture? The second? The second session with Professor Kimura, intrapid neuropathy and mononeuropathy of the legs with Professor Kimura.
Thank you very much. I brought slides from Japan. These are the girls I went to school together. That's a long, long time ago. But you know, I actually live in Japan. I live in Kyoto, and I work in Iowa. So it's a long commute. But you know, that's what I do. Okay, so this is the entrapment neuropathy, which we're going to demonstrate later on this morning, right? But just get you familiar with what we're going to talk about. Let me show you five principles that we have developed over the years in Ireland.